The resulting frequency response is obtained with this frac C. So we're plotting the frequency response from the impulse response we obtain here for the minimum phase filter. And this is the frequency response of the minimum phase filter. Now, if we compare the above frequency response of the minimum phase with the linear phase, plotted here, we can see that the magnitude is about the same, except from an offset of about 5 dB, which is not so important because it's a constant gain factor. But looking at the phase, we see that the minimum phase has less phase lag. This is the minimum phase, and this is the linear phase. So looking at normalized frequency 1.5, we see that the linear phase filter has a phase lag of about -7 rad. So at 1.5, so no, this is the linear phase, so 0 -7. Whereas the minimum phase has a reduced phase lag of about -5 rad. So 3 -2, so -5 rads. If we take the derivative of the phase function to obtain the group delay, we will get corresponding lower values, which means that the minimum phase filter will have less group delay than the linear phase filter. In fact, it has the lowest possible delay for the given magnitude response of the filter. So if you have a given magnitude filter design and you want to obtain the lowest possible delay, you have to take minimum phase filters. Also observe the phase drop around points. They are not always at plus or minus pi, but in other cases where the magnitude has zero crossing, where the phase is not well defined. So a convenient SciPy function to obtain a minimum phase filter with a similar, not exactly the same magnitude frequency response of a linear phase filter is this SciPy signal minimum phase. So here you can take a look at the help function. So it takes some arguments, it returns the minimum phase version of the filter. And as an input, it expects a filter with the square desired frequency response, which we can obtain by convolving the linear phase filter coefficients with itself. So in our example, an approximate linear filter is obtained by if we convolve H-sync with itself, and then we get this, we call this minimum phase function from SciPy with this squared, so it's this convolved by itself. And when we plot the frequency response, we have here the magnitude looks the same, but the phase looks different because it starts at 0 instead of pi as before. And this is because the filter coefficients here have a switch sign, and this is no problem because we can always change the sign by multiplying the filter or its output by -1. So when we compare the coefficients by looking at them, we see that the coefficients are similar but have indeed opposite signs.